So good morning, everyone. My name is Christopher Jout. I'm Head of Technology and Government Relations with Waterloo Biofilter Systems. Today I'll be presenting on a pilot demonstration project we did with edge of field phosphorus removal from agricultural runoff. So my presentation today is going to cover the Waterloo ECP technology, what it is and how it works, go over the PRC pilot demonstration results, and talk about scaling up the technology for future implementation. So the Waterloo ECP technology, this is a new strategy for the permanent removal of phosphorus. So I think we're all familiar with the conventional strategy in wastewater removal, separation of a phosphorus-rich sludge via chemical addition. So adding a chemical to form a flock. Typically you have to add another pH buffering chemical, and this phosphorus concentrated sludge is eventually pumped out and sent to the wastewater treatment plant where it needs to be retreated again. With the Waterloo ECP, we're doing a new strategy of the precipitation of iron phosphate minerals. So with this method, there's no chemical addition, there's no sludge production, no change in the pH, and there's no need to subsequently retreat the phosphorus at the municipal plant. We also have the ability to recover the captured phosphorus as a fertilizing soil amendment. So closing the loop on the phosphorus cycle. This is a patented process. So what we're doing is we're mimicking the way phosphorus is removed in nature. So in naturally iron-rich B horizon soils, phosphorus leaches down and is adsorbed onto the iron hydroxides found in the soil. It's eventually mineralized as insoluble crystalline mineral cements such as vivianite and strangite. With our Waterloo ECP technology, we're taking natural iron electrodes, passing a small current between them, and basically dissolving the electrode into the water to create iron phosphate ions. These are passed through an aerobic filter media, be it foam, sand, soil, or our silicate-based phosphorus recovery media. And in there, the phosphate iron minerals are precipitated as crystalline mineral cements, where they're insoluble and they're not going to be leached out if the geological conditions change. So basically what we're doing, to summarize, is we're taking an otherwise non-reactive filter media, such as clean foam, clean sand. We're adding iron to go straight to the mineralization step, where we can consistently remove phosphorus over time. So we've done a lot of work in the past with this technology. These are SEM scans that show that we are forming these bladed crystalline structures. These are SEM scans of the foam treated with ECP. You can see that the pink color is where iron is located, and the blue color is where the phosphorus is located. You can see that the two are very well correlated. So wherever there's phosphorus, there is now iron. Zooming in on the bladed structure in the bottom there, XRD scans do verify that this is the mineral vivianite being grown inside the biofilter. So this project itself is a new application of this existing technology. So the Waterloo ECP was designed for the on-site wastewater market, where we can get 95+% total phosphorus removal. This is in lower loading rates because there's a lot of obviously organics in wastewater, and the wastewater is typically higher total phosphorus concentrations, lower dissolved oxygen concentration environments. In agricultural runoff service waters, this is a new project for us, so unknown. To make anything economically feasible out there, we have to do higher loading rates through the system. So that's feasible because there isn't the organics to deal with that you find in sewage, but it is a very low total phosphorus concentration and high dissolved oxygen environment. There's also other considerations to take into account, such as an abundance of silt in these agricultural runoff areas, year-round operation throughout the winter without freezing, and we are drawing from surface waters, so there can be no flow periods. So PRC pilot demonstration. So just to go over what the program was, so the Thames River Phosphorus Reduction Collaborative. This is an alliance of farming organizations, municipalities, First Nations, conservation authorities, and other NGOs and others. It's led by the Ontario Federation of Agriculture and the Great Lakes and St. Lawrence Cities Initiative. The group was formed in 2016 to come up with a strategy to deal with toxic algal blooms in Lake Erie. So this program itself was a call for proposals to demonstrate in-field phosphorus removal. And the demonstration program itself was funded through the Environment and Climate Change Canada's Great Lakes Protection Initiative, as well as the Canadian Agricultural Partnership. So our demonstration site was the Boudreau Pump Station. This is located 15 minutes southwest of Chatham, Ontario. The pump station services 340 acres of tiled land that is in row crop production. And from this ditch that's pumped into the municipal, the drain pumps into the Jeanette's Creek, which ultimately discharges into the Thames River. So the picture here shows the actual graded screen ditch that we're drawing the water from. We did have historical data on the quality of water in this ditch, which we used to guide the design of the demonstration site. So historically, they saw about a half a milligram per liter total phosphorus, 0.2 milligrams per liter reactive phosphorus in this ditch with very high TSS, so averaging 176, but upwards of almost 2,000, and that's likely due to the silt runoff. So that was a big concern for us in the design of the system, was handling the silt. So it is a containerized system. It's housed in a 40-foot shipping container. The first two tanks are simply there for settling, to try to reduce silt from reaching the filtration stage where it has the potential to plug things up. A third tank houses our Waterloo ECP electrodes. That's a total of 12 of them. From there, the water is pumped and sprayed over to Waterloo biofilter treatment units, one being topped with our silicate-based phosphorus recovery media. The whole tank gravity drains to a disposal tank, which in this was then pumped out to the Jeanette's Creek. So the influent sample we're taking directly from the force main within the container itself. The effluent sample we're taking from the drain. As you'll see, we went to augmentation of incoming influent due to very low total phosphorus concentrations with the permission of the PRC. So for those samples, we started dosing a high phosphorus liquid fertilizer, very small amount, into the first settling tank, taking the phase 2 influent samples from the second settling tank only for the nutrients, nitrogen and phosphorus. So this slide shows some of the other components of the system. Due to the high amount of silt in the water, as well as we know this is a surface ditch, the water level in the ditch is dependent on rainfall. It's moving up and down. So we have a floating suction intake that basically is a floating ball on the surface of the water. So it makes sure we're always drawing from the top 8 to 12 inches underneath that water. So we're not taking stuff off the top, but we're not taking stuff off the bottom as well. The whole system is controlled remotely with a smart panel control. This allows you to remotely log in and download data, remotely change system settings. The 12 electrodes suspended in the ECP tank. This picture shows them after the 15 months operation of the project, after which they had lost approximately 55% of their initial mass. So the two foam biofilter tanks, one is just the normal foam cubes. The other one is topped with our phosphorus recovery silicate-based material. And as to be expected, we're adding iron, so over time everything in the system starts turning orange. So these are the results from the pilot project, starting with total phosphorus. So note this is in a log scale here. Total phosphorus in the phase 1, we saw very little coming in, about 0.11 milligrams per liter coming in. That was reduced 35%. There's very little reactive phosphorus at this stage. In the phase 2, which you can see starts with the red line, when the phosphorus augmentation begins, influent, we were aiming for between 1 to 2 milligrams per liter in the influent. total phosphorus removal increases to 66%. Of the reactive phosphorus portion, initially in phase 1, and this is the reason why we ultimately went to the augmentation, there's practically zero reactive phosphorus coming in. I think it averaged 0.04 milligrams per liter and 0.03 coming out. So 21% reduction, but we're down near the detection limits of the laboratories. After the augmentation begins, reactive phosphorus increases and we're removing almost 90% of it. This slide shows the total phosphorus percent removal versus the hydraulic loading rate of the biofilters in the system. So that's expressed in liters per cubic meter of filter media per day. So as to be expected, the lower loading rates typically have the higher percent removals. So the slower you're putting water through the system, the better the removal rate is. The faster you're moving water through, the worse the removal is. This slide also shows some of the different stages we went through. So we started off with lower flow rates and 4 electrode equivalents running. So basically 4 of the 12 electrodes running 24 hours a day. That was increased to 6 electrodes per day and 8 electrodes per day total. So you can see that the lower hydraulic loading rates and the more electrodes running, the higher the percent removal. Energy usage of the system was monitored. So we start off under 1 kilowatt hour per cubic meter of treated water. When winter comes, we turn on space heaters to keep everything in the shipping container from freezing. That's obviously, it will increase your energy usage. In the spring, that's turned off when we go back down to less than 1 kilowatt hour per cubic meter. In the summer, we started to see our flow rates decreasing and our energy usage increasing. So the influent pump drawing from the ditch is working harder and taking less water. So we start to see the energy. We thought that the influent pump was starting to fail due to the silt in the water. We replaced it. That had no effect. We cut into the intake line and found that there was growth in the intake line coming from the ditch. So once that was flushed, then everything went back down to normal. Energy usage went back down to less than 1 until, again, winter hits and the heat tracer is turned on. So this chart shows the daily flow rate on the system. We started off at 20,000 liters a day. After a few months of operation, we increased it up to 40,000 liters a day, which was what the system was designed to handle. After time, the intake line started to plug. We saw the flow rate starting to plummet. Once that intake line was flushed, we went back up to the 40,000 liters a day. Overall, the system throughout the entire project averaged 27,400 liters a day. The times where the pump, where you can see zero flow rate, was either, I think the first one was the pump lost prime. The next couple in this past fall, there's no water in the ditch. On this slide, we can see the results of the project. The total phosphorus in phase 1 is averaging 0.117, reducing 35%. If you think back to the historical data on this site, they had seen 0.5 milligram per liter going in, 0.2 milligrams per liter reactive. We saw basically no reactive coming in. The effluent's pretty much at the detection limits. So in phase 2, when we're increasing the phosphorus, influence up to 2 milligrams per liter total, we're removing 66% of it. We're importantly removing 88% of the reactive phosphorus and 88% of the dissolved phosphorus. We did monitor for another of other parameters. Dissolved oxygen increased almost 30%. There was practically no change in the pH. The temperature increased throughout the system 1 degree Celsius, and TSS was reduced over 50%. You can see the TSS number that we saw was much lower than what the historical water quality was. So whether that's because we're drawing from the top level with that floating suction intake, reducing the silt, reducing the particulate phosphorus into the system versus where they're taking their sample, potentially from deeper. Conductivity was basically unchanged. Turbidity was improved 17%. Total nitrogen is practically unchanged, and we did increase the total iron by almost about 100%. Now, about half of that increase in total iron is due to the phase 2 dosing of the fertilizer, which does have a bit of iron in it. The other half is due to the electrodes. Now, in the future, in practical use, that can be more optimized than what it was here. For example, throughout the summer, the electrodes are running based on, we're seeing 40,000 liters a day through the system. As we saw earlier, we were seeing less than half of that at times. So the electrodes could be timed into the actual flow rate of the system, better to reduce any excess iron. So how this system would scale up for future implementation to help tackle some of the algae blooms problems. A full-scale containerized ECP system would be housed in a watertight container with 2 insulated watertight compartments, a 2-foot control panel room housing all the controls. It would have roof access hatches. We found that we had too much upfront settling tanks. After 15 months operation, those 2 tanks in the demo project had 4 to 6 inches of sludge in them. So again, because we're drawing from the top level, we're reducing the amount of silt coming in. So we would have less upfront settling and basically baffles only. You could also have pump outs, and if you do have a lot of silt or sludge, you can pump that out to a dewatering bag if needed. So basically with this type of arrangement, we can fit a 100,000 liter a day system into one 40-foot high cube shipping container at about 40 to 60% total phosphorus removal. Now for the PRC project, what they're looking for is 40%. 60% is kind of the average of what we saw at the loading rate to get 100,000 liters a day in. So in the chart here, you can see the orange line indicates the loading rate to get 100,000 liters a day into that container. It starts at 40, goes up to 60. So that's well within the range of percent removals that we saw. Okay, this slide shows the cost of phosphorus removed. So in terms of kilograms of phosphorus removed, what is the actual cost? So this is broken down for us in terms of energy and electrode consumption. Now the biggest variable in this is what the influent concentration is going to be. The electrode cost per kilograms removed is, theoretically it's consistent. If you have a low concentration influent, you run the electrodes at a lower rate. If you have higher concentrations, you run them at a higher rate. Over time, they still need to be replaced. It's all dependent on what the influent is. Energy is the big factor. So, whether you're pumping 100,000 liters a day through and you have 0 phosphorus or 1 milligram per liter of phosphorus, that's the big contributor to the cost here. So this is broken down. The blue line is the electrode cost. The energy line is orange, and the total is in gray. You can see that at about half a milligram per liter total phosphorus, the total cost is about $500 per kilograms of phosphorus removed. Excuse me. When you get out to 1 milligram total phosphorus on the influent, you're down to 300, and then we're crossing below $200 a kilogram removed at 2 and above in the influent. Okay, so with the Waterloo ECP system, we also have the potential for phosphorus recovery. We can close the phosphorus cycle. So using our silicate-based material I've mentioned before, we use it as an initial filtration media. So the water that has the ECP treatment goes through the silicate-based material first. After a number of years, this media is removed, replaced. It's mixed in with soil as a fertilizing soil amendment. Now, we've done work with the University of Guelph in the past. They did greenhouse corn growth studies, looking at soil only or a control, the silicate material only, superphosphate fertilizer, the silicate material and septic tank effluent, and then finally the silicate material septic tank effluent with the ECP. They did 15 plants of each of these 5 treatments. So what they found was that the ECP treated plants had the highest phosphorus uptake, the tallest plant height and the most biomass, even compared to the superphosphate fertilizer. So this slide shows you what a full-scale containerized Waterloo ECP system would look like. And there's basically two types of process configurations. We could do a final polishing like we've done here. This is actually the site we're drawing from the ditch there, pumping into Jeanette's Creek. You can also do it on a closed loop dilution for something like a sewage lagoon. You're drawing from the water, reducing the contaminants, and putting it back in. So other potential applications for this technology would be other surface water, so obviously agricultural runoff, wastewater lagoons, stormwater retention ponds, other large ditches. Also, we can do point sources. Now, this would obviously be at lower loading rates because those are typically higher concentration and usually with other contaminants in there. So anything from individual septic systems to communal subdivisions, small villages, liquid manure, and other processed waters. So just to conclude here, so we found from this project that the Waterloo ECP technology is suitable for these low phosphorus, high dissolved oxygen environments and has good potential for the phosphorus removal from surface waters with very, very high levels of reactive and dissolved phosphorus removal. So very little impairment to background water quality. We did increase iron slightly, but as I mentioned, that can be more efficiently optimized in the future. Other parameters were increased. The system overall has low energy requirements, successfully operates year-round without issues, and can withstand periods of no flow without damage. A big question for us was the silt in the source water, and we found that this can be successfully managed. And again, we do have the potential for recovering the phosphorus as a resource. So thank you for your attention, and I look forward to fielding any questions in the next session. Thank you.